Okay, silence, so people want to start. So we start with the last two talks of this afternoon session, and the first one is by Cameron Morgan, and it is about decoding the quenching in the Virgo cluster with spatially resolved star formation. Please, take it away.
Great, thanks. So my name's Cam Morgan. I'm a PhD student at the University of Waterloo working with Michael Ballo. And I want to chat a bit today about sort of the first part of this project we've undertaken, which is trying to decode the quenching sequence of galaxies in the Virgo cluster by looking at spatially resolved star formation. So of course we don't need too much intro into the Virgo cluster. We've already talked about it a few times today. But just to give a bit of background, Virgo is a great cluster for us to try to do a study of spatially resolved star formation because of course it's so nearby. And so some recent surveys with NGVS being a deep optical survey of the entire Virgo cluster, and then Vestige being a narrowband H-alpha follow-up to this, have given us really deep and high-resolution imaging in these different bands that we're using for this project. So of course, we've talked about ram pressure stripping in Virgo. I don't want to get too controversial about it or anything, but we have seen ram pressure stripping in Virgo. This is from a recent review from Baselli et al. We see the galaxy on the left with the H1 contours of this stripped gas, and the galaxy on the right where the red is showing the H-alpha emission and the stripped ionized gas. So we know this is something that does happen in Virgo, at least to some extent. However, we're a little bit curious about what's happening in sort of the outer regions of the Virgo cluster and in some of these smaller groups and other structures that sort of surround the main cluster body. And so if I show a projected phase space plot here of the whole Virgo environment, and the grayscale is showing the quench traction. And so this is, for the most part what we expect, where in these ancient infall regions we have mostly quiescent galaxies, with the virial radius being here and these contours showing the escape velocity of the cluster. But we do notice that there are, reasonably high, in some cases, quench fractions even in the outskirts of the cluster. If we look at something like ram pressure stripping, and we model this by looking at the ICM density of the cluster compared to the restoring force of the galaxy that's holding on to its gas, we find that ram pressure stripping can probably only dominate in Virgo close to the cluster center. Of course, this depends on the mass of the galaxy and the exact profiles of the different components of the galaxy, but to some median amount we would get a contour like this red one here. And so an infalling galaxy cannot be stripped close to the virial radius necessarily. However, we do look into this region in the outskirts, and we find that there are some galaxies here that are already quenched, and there's also a lot of galaxies that are a little bit gas deficient and are sort of starting to fall below the star-forming main sequence. Some of these may be backsplash galaxies that have already passed through first pericenter, but it does look like some of them are on their first infall, and it sort of begs the question, what is starting to quench these galaxies in this region? And so we turn to other quenching mechanisms, namely something we haven't actually talked about as much so far because it's a little bit more boring, but this is starvation. So we think about a very kind of simple toy model of starvation here, where a galaxy prior to infall into the cluster is forming stars out of its gas according to the Kenniket-Schmidt relation. And it's sort of in this steady state where its molecular gas is being replenished by its H1 reservoirs, and that gas is being replenished through accretion and so on. And then we assume that below a certain threshold gas density, the star formation sort of truncates. And this is sort of going back to the idea that in that low gas density regime, the Kenniket-Schmidt law kind of turns off. And so if we look at the schematic on the right, we see that if you have some gas density profile, which here is just in exponential in log space, at some point this is crossing below the star formation threshold. Then as the galaxy falls into the dense environment and has accretion cut off, which again for simplicity here we assume that it can no longer accrete any gas at some point along its infall, its gas density profile will start to sort of globally decrease, or at least again in the simple case it would be a global decrease like this. And as this proceeds then, the point at which this gas density profile falls below the star formation threshold moves radially inward. And so by this, with this sort of model here, we would expect that something like starvation could actually truncate the star-forming disk of the galaxy. Of course, though, this would be on much longer time scales than what we think something like ram pressure stripping would do. Again, these times, of course, depend on the exact nuances of your starvation model. But we expect this to be something that's a bit slower. But if we assume starvation can begin prior to first infall, potentially in these smaller group structures that we see around Virgo, then we see that the galaxy could begin losing some of its gas, could start to truncate its star-forming disk before the point at which ram pressure stripping would take over as it falls into the cluster. So then, of course, we need to go and actually look for, well, do we see these truncated disks in Virgo galaxies? And so we do this by taking our H-alpha imaging from Vestige and constructing star formation rate density profiles, which you can see in the black here for this example galaxy, and then using the optical data from NGVS and Vestige to construct stellar mass surface density profiles, which you can see in the blue. And we can already see that there's sort of, in this case, this sort of truncation in the H-alpha profile, but we can see this even more if we then construct a specific star formation rate profile. So we take our star formation rate density and divide by our stellar mass surface density, and we get this radial specific star formation rate profile. And we expect that, without any sort of inside-out quenching going on from something like an AGN, our specific star formation rate should be relatively flat in the inner regions, and then at this sort of truncation point, we get this rapid falling off. And so we identified these points in these Virgo galaxies. We have about 350 of them, and we call this our trunk. But now we sort of need a way to quantify sort of the strength of this truncation, and so we come up with an estimate for how big we expect the star-forming disk of a galaxy to be if it's not undergoing any quenching, if it's just living on the star-forming main sequence. And I don't have the time to go into the details of exactly how we do this, but of course I can chat about it with anyone later. And so once we have this R trunk and this R norm measurement, we can sort of take the ratio of the two and then get an idea of how truncated the star-forming disks in these galaxies are. If we take a look at some images of galaxies, a couple examples here. So I'm showing the H-alpha images, continuum subtracted images on the left, the R band in the middle, and then the specific star formation rate on the right. The green ellipses show this R trunk value, and we see that at least visually it traces the H-alpha extent quite well. And similarly, R norm with the red ellipses traces the optical emission quite well. So one thing we find is that truncated disks are pretty much everywhere across the Virgo environment. So this is the footprint of the Virgo cluster, showing the main cluster region as this largest circle, but then some of these other subclusters and smaller structures as well. And if we're looking at galaxies that have, an R trunk over R norm value of less than 1, or ideally, much less than 1, we see that, these galaxies are pretty much everywhere, including in these infalling groups. And so if I bring up this phase space plot again, but now I'm going to change the grayscale here to be, instead of the quenched fraction, the density of substantially truncated disks in Virgo, we see something kind of a bit interesting, which is that the densest region of truncated disks is in fact in this region that appears to be sort of in the infall region of the cluster, outside the virial radius. And as I said before, many of these galaxies we can see are starting to quench. They've lost some of their gas. They're starting to fall below the main sequence. And so if ram pressure stripping cannot dominate in this region, maybe it's possible then that with this starvation model, starvation is sort of giving a kickstart to the quenching in Virgo. And this sort of follows the idea of like a delayed then rapid or slow then rapid quenching sequence, where starvation sort of begins quenching again, possibly prior to first infall, depending on the environment of the galaxy at that time, and then ram pressure stripping maybe takes over later, closer to the center of the cluster, closer to first pericenter, and then sort of rapidly quenches the galaxy, truncates the star-forming disk at that point. Now I said this was sort of the first part of a broader morphology study that we are conducting, so this is sort of our first parameter that's giving some hints at which mechanisms may be dominating in different regions of Virgo. But what we really want to do here is take advantage of the spatial resolution of this survey, of the Vestige survey, and try to quantify in some ways the different morphologies we see in the star-forming regions and how they're distributed across these galaxies. So as an example here, this is a galaxy in Virgo that clearly is undergoing ram pressure stripping and has a strip tail, and also possibly this like leading edge induced star formation, something we've talked about a little bit as well. And so if we can sort of quantify these morphologies in some ways, we can get more insight into how gas is being consumed and or stripped away in these galaxies with these various processes. So I'll wrap up there. I'll leave my summary, and I'm happy to take any questions.
Thanks a lot. Question there.
It's a very nice camera.
Thank you.
I don't think I heard you talking about a phase of enhancement of star formation in these galaxies. Do you see any evidence of that? And what kind of star formation history do you think you get, like in different parts of the phase space?
Yeah, that's a good question. So that's kind of something we want to look at with this next bit of the project here. So we're trying to find some a little bit more niche ways of quantifying this morphology to find things like possible enhanced star formation, and then see if that depends on where the galaxy lives in the Virgo environment. We didn't really look at that too much with the radio profiles, because I think that's something we want to do, taking advantage of the whole 2D imaging and the resolution we get there. But yeah, that's definitely something we're looking at.
That was a great talk. So you assume for the starvation that all the gas gets kind of uniformly depleted, but is that still a good assumption? Because when you have galactic fountains, the gas may not get redeposited on the disk uniformly with radius. So do you know how that would affect, accounting for that would affect your interpretation?
Yeah, so we kind of played with a few different models. Again, this is obviously an oversimplified starvation model, and the nuances of, gas conversion and as you said, things like the galactic fountain and that would obviously change the sort of timescales or exactly what we see. So the way we did it here was more meant to just be this is something that we think can happen, and obviously the shape of the gas profile will change what kind of truncation you get. But yeah, at least to first order, we think, the truncations can happen, but obviously the, parts of the way you model starvation would change exactly how it happens, yeah.
I'd like to make a small comment. Not all galaxies of Virgo are info in isolation, but they info in groups. Actually, the talk Xu Cheng gave on Tuesday, he showed a study of NGC 36 group. That's a group infalling into Virgo currently at a distance twice a Virgo radius.
Yeah, absolutely, and that's I think something that obviously the one phase space plot just showing relative to M87 doesn't capture all of that information, but I think looking at these infalling groups, and that's sort of something we want to follow up on as well to see if that's that could be part of the reason something like starvation might begin early, right? Well, prior to falling into the main cluster.
Actually, ram pressure stripping also start earlier.
Yeah, exactly, and there might even be some ram pressure stripping there. So yeah, that's what we're going to try to figure out with this next phase here. Yeah, thanks.
Do you have any galaxy that you can use as control sample to even in the outer region?
Yeah, so in this case, we think that all the galaxies in this sample are probably being affected by the Virgo environment in some way. So the one thing we don't have is an exact control field sample to look at this. We do find that like the more, galaxies that are not gas deficient in Virgo do have, less truncated disks, like the R trunk of R norm is closer to 1, but it could benefit from a more robust control sample for sure, yeah.
We are done. Next speaker. Yes, please. You can. Is there another last urgent question while we are setting up? No. Then we thank Cameron again.
Thank you. Oh, you want that? Yeah.
The last speaker is Andrea Biviano. Ram pressure stripped galaxies move on very radial orbits in clusters. Clear statement.
You already spoiled my result.
You put it in your title.
Oh, really? So I guess some people of you might not Where is this? Where it is? I can't see it. I can't see it. Okay, so I guess not all of you would just trust me on my word, so probably even if you're tired, I have to convince you that this is indeed the case, that round pressure strip galaxies move on very radial orbits in clusters. I'm Andrea Biviano, and this is a collaboration with the GASP team. So the motivation for this study comes from the theoretical understanding that the efficiency of round pressure actually depends on the galaxy orbits, being stronger for more radially elongated orbits, coming from theory and numerical simulations. And there's been actually previous results that have given some indication this is indeed the case. But what we're doing here is actually trying to determine the orbits of round pressure stripped galaxies by the application of the Jeans equation of dynamical equilibrium. So the data set I'm using it comes from Bianca and from Benedetta, and so you might ask them, they know better than me what they are. Basically, it's a sample of candidate galaxies for round pressure stripping. After removing the most probable examples of tidal and merger features, we end up with a sample of 350 round pressure strip galaxies with redshifts, which belong to 68 nearby clusters. We take the cluster center as the BCG positions, and the mean cluster redshift and the dynamical parameters, the mass profile of these clusters, are taken from previous dynamical analysis that I've done, the same collaboration basically. And in the end we have this 68 cluster, low redshift and pretty massive. And what we have to do is to assign membership of the galaxies with redshift to these clusters. And membership assignment in clusters is not trivial in general, so it's bound to several systematics. So what we're going to do is, what we did was to consider 3 different techniques to assign membership, which I'm not going to describe in detail, but they're pretty different in spirit. So what we do in the end is that we decide that the galaxy is a member if it satisfies at least 2 of these techniques, okay? In the end, we have these 285 candidate clusters in the 62 clusters remaining. And of these 285, we only use the 244 which reside within the virial region of their cluster, where the virial region I define like R100. And of course, with with 245 galaxies divided by 62 clusters, you can make the arithmetic. There are not many, so you cannot really do that Jeans analysis on a cluster by cluster basis. What you have to do is stack. And the usual way to stack in clusters in this game is to use R200 to stack on the radii, the distances of the galaxies from the cluster center. And V200, which is basically the same thing, so it's just one parameter, to normalize the velocity, the rest frame velocity of the galaxies, with V200. So what you end up in is this ensemble cluster projected phase space, rest frame velocities versus distances from the cluster center in normalized units. Here the contours are all members. And the dots are the round pressure stripped members. You can clearly see already here that the distribution of these members is different from the overall distribution of the overall cluster member population. For the analysis, we have to solve the Jeans equation for dynamic equilibrium. We used 2 techniques, which again I don't have the time to describe, but if I do, you would be bored to death before we go to the dinner, so I won't go into do that. So it's Mampost and J. They are again different in spirit. Mampost used models for the mass distribution, for the velocity anisotropy profile. J instead is built up from the data by smoothing, essentially. What is important here is that we do have the mass profile already in this game, because the mass profile of the ensemble cluster is we can take as a weighted average of the individual mass profile of the different clusters, which we derived some years ago, of course in that case by using all the members, right, as traces. So we end up, well, we assume it's NFW for simplicity, and we end up with these values, and as you see, they are pretty massive, R200 1.6, and the concentration, as you see by dividing these two values, is what you expect for nearby clusters of this mass, around 4. But then the other parameter, the other quantity you have to insert in the Jeans equation is the number density profile for the tracer for which you're trying to determine the orbits, which are the RPS galaxies, round pressure stripped. And what we find out is that their number density profile is this value, which is even, the scale radius even larger than the virial radius. So they clearly have a scale radius not only much larger than the overall cluster members, but also much larger of the mass distribution, okay? Right, now what we are after? What we are after is this quantity, this profile beta of R, which is essentially 1 minus the ratio between the velocity dispersion along the tangential component and velocity dispersion along the radial component square. It's a pretty intricate way to describe the ratio of these two quantities, but it's what's been used in the literature. The range is also pretty strange, between minus infinity and 1. When you have beta greater than 0, you have a radial orbits, something like a comet in the solar system. Or if you have beta less than 0, you have more a tangential orbits, which is more like a planet in the solar system. Equivalently, in this talk, I will also use the ratio between sigma r and sigma theta. So when sigma r is greater than sigma theta, you have a radial orbits, okay? Okay, this is what we are after, and by the Jeans equation, once you have the mass profile, the number density profile, you can solve for, and the observables, of course, you can solve for this beta of r. But before I show the results, I can show that the results make sense, because the analyses do not necessarily converge to a solution. Especially with MAMPOST, it's a maximum likelihood analysis. You get the best model parameters, but that doesn't mean it fits the data. So this is shown here that our solutions, when you project the solution on the space of observables, it does fit the data. In this case, the space of observable is the velocity dispersion profile along the line of sight versus distance from, the velocity dispersion versus distance for a cluster center. The data are these stars for the round pressure strip galaxies, and the model predicts the solution for these two, the J and the MAMPOST techniques are in blue and in red. They agree with one another, and they also agree with the data. So apparently the solution makes sense. So at this stage, you can trust me, and don't ever trust me completely, but sometime, trust me, this is the result that we find for beta. And as I said, if it is above 0, we have radial orbits. And you see that indeed round pressure strip galaxies have radial orbits from the center to outside. Well, MAMPOST goes here to negative values, but the data stops here. MAMPOST use models, so it's an extrapolation. So overall, the error bars are pretty large, as you expect for this size. And the interesting thing is that not only the RPS galaxies have radial orbits all the way, so essentially, becoming even more radial outside, but they have more radial orbits than the spirals. Now, the spirals, it's a work we have done with Gary Mammon, more or less on the same data set, okay? Of course, spirals do include the round pressure galaxies, but they are a minor part of them. So, okay, this is the point. I'm not showing here the ellipticals and S0s, but they would be even closer to 0 here, as I show in this other plot. This is, since in Mamon et al. 2019, we only use MAMPOST. I'm using the results for the MAMPOST model. Now, in MAMPOST, we use this parameterization for the beta profile, where you have the central anisotropy and the anisotropy at infinity on the vertical axis. And so basically what you see here is that ellipticals, zeros, spirals, and RPS, they are all very close to isotropic orbits near the center, or even tangential orbits for the ellipticals. But then when you go outside, the early type galaxies remain very basically isotropic. The spirals become more anisotropic, and the RPS, well, even if they are well within the error bars, they are apparently even more anisotropic. I mean, the ratio between these two quantities goes to 6. Okay, so I have a slide on systematics, but this will definitely bore you to death, so I'm not going to talk that, unless you really want me to talk about that. The main systematics are the assumption of dynamic equilibrium we can imagine for RPS galaxies, and the reliability of RPS classification. You can ask me. And so just my conclusion slide, which is very synthetic.
Thanks a lot. Questions? Jarne, sit.
Very nice, Andrea. So, so in this case, would you get, if you run a model without velocity anisotropy, do you get a significantly worse fit?
Yes.
Okay.
It doesn't fit.
So it doesn't fit at all. Okay, that's reassuring. But then the second question is, you don't have motion in the plane of the sky. So what degeneracies do you have in the solution?
Well, generally, this could be a serious problem. Triaxiality, basically. Clusters are not spherical. It's much less of a problem, or even not a problem at all, when you do stacking, because stacking basically constructs a spherical cluster by definition, by construction. It's been shown in van der Marel et al. 2000, many years ago, that this is actually, apparently works.
Andrea, curiosity, have you done the same test, not by morphology, but just looking at all galaxies that are on the main sequence?
Well, not on the, you mean you're referring to ellipticals, zeros, and spirals.
Yeah.
This is the paper of Mamon, Cava, Biviano, and others. No, we are using morphologies, but this is an interesting question, because when you go to high redshift clusters, generally you build upon colors or on spectroscopic classification, and results are not always fully consistent. I would say that apparently the early time morphologies seem to have more isotropic orbits than the red passive galaxies. And this is something I want to explore sometime, but never found the time to disentangle these two things.
I was wondering, can I extrapolate your result in saying that the vast majority of first infallers are on radial orbits?
Yes.
Okay.
But in fact, this is pretty much consistent with what you see in numerical simulations, even for dark matter particles. The crazy thing, I would say, is the difficult thing is to explain why ellipticals and A0 have such isotropic orbits, even a large hair radii. This is not trivial.
So I'm just curious, would your result imply that the tails are preferentially oriented towards or away from the cluster center? And is this a scene in GASP?
Okay, there's a poster over there about this, and yes, they are preferentially oriented away from the BCG radial direction. If I can remember correctly, I'm a co-author. I'm the number 45 in the list, so I don't remember exactly. But yeah, what's the name? Vicente Salinas. And, but overall, you have to take into account that there is a projection effect, right? So when these galaxies are close to the center and they are moving around the center very close, you can see even something which is completely orthogonal.
Okay, any last urgent question? No. Then we thank Andrea and all the speakers. For all these excellent talks and being perfectly on time. Now I give the microphone to Bianca, who has important things to say.
Well, no, just to say, okay, let's not, lag behind. Take your stuff and follow Alessia and Marco. Alessia and Marco will show you the way. Okay, Alessia.